A construction project, it's not fun. For years, this disruption to day-to-day life. As a citizen, when your street is blocked for 10 years, they're super expensive, super long, and they're never on time and never on budget. Never. Highways, tunnels, metros, light rail systems, electric car infrastructure, new power lines, new electric stations. There's a taxpayer interest that those projects finish on budget.
Jeremy Suard, founder and CEO of Exodigo. Sounds like Excalibur, so I love it. Thank you for making the time. I know you're in Miami now. Your company works with transit authorities or construction developers, builders. You are in the construction industry, that is the building industry. How does building construction look from space?
So from space, you can divide construction, I think, into two different pieces of construction. One is private, which would be buildings or houses. And the other one is infrastructure, which is financed by government. It's completely different worlds. Nothing links them. Not even the companies that do that, not how it works, not where the budget comes from, not where the incentive, and not how complicated is the project. So we're currently active in the infrastructure construction market.
The infrastructure construction market is trains, rails, utilities, water companies.
It's utilities and transportation. Basically anything that's being built that's big and that is being built in the public right of way and not a private area. It's huge. Highways, tunnels, metros, light rail systems, electric car infrastructure, new power lines, new electric stations, because there's a need to switch to net zero now and there's a need for electricity everywhere, new gas pipes because they're getting old, replacing the water pipes. All those types of projects are in the end financed by the public sector and they're being built in your street, which means in the public right of way. So those projects, they're super expensive, super long, and they're never on time and never on budget. Never. And there's a couple reasons why. Number one reason is politics. Number two is bureaucracy and permitting. So this we can't really help. But number three is unexpected underground issues. Unexpected meaning you discover way too late that what's there is not what you thought, or designed on, or built the entire contract on. They thought they were going to dig in sand and in the end it's rock. Or they thought that all the power lines were removed out of the way and suddenly there's 5 power lines that was going to take 4 months to remove and the whole project stops completely. And so unexpected issues due to underground are one of the major reasons that projects are never on time and never on budget. And that's the problem we're coming to solve. You know, if a company is asked to prepare a proposition for digging in sand, they'll give you one price. I don't know, $500 million. Suddenly it's rock. Okay, now it's $1 billion. Who pays for the additional $500 million? And those are the amounts. Those are the sums. So basically it's, you thought there was something and it's something else.
Wow. I just want to unpack that a little bit. We all intuitively feel and know that construction of any kind, whether it's even private or government, is always over budget, always over time, never efficient. It would be a massive shock if a big train
is built on time.
Train line is built on time or anything, right? It sounds like you were saying that there are 3 buckets of things that
main ones.
One, main ones, right? Really, really tough nuts to crack. And one of those is politics, and we can talk about that. The second one,
bureaucracy.
Remind me? Bureaucracy, which is tied to politics because...
Yeah, but politics is really politics, and bureaucracy, it's between agencies. So that it doesn't have anything to do with the public. Like, who's the president is politics. What are the bureaucratic elements in an organization? How do you do permitting? How are things authorized is bureaucracy.
Yeah. Okay. And then once those things actually get approved, eventually there's a timeline, there's a project timeline, there's a project manager, there's just a whole armada of people and supply chains now geared and contracted for this thing. Then there's a third problem, which invariably happens, which is we didn't do the surveying.
They
properly.
Don't have technology available today to do a good survey of the underground. And so there's always surprises. And those surprises change the fundamentals of the project sometime. Can be a couple months delay. A couple month delay can cost $100 million. or it can be years of delay if suddenly the entire project assumptions are wrong. It happened. So there's really bad stories and there are less bad stories, but the range is bad.
Give me a really
I'll
bad
give you
story, and then give me a worse story.
I'll give you a very bad story and then a worse story. Very bad story,
Okay.
Sound Transit, which is the transit agency of Seattle. So there was a project that ended up costing 220% of the cost and took 3 times the number of years because of underground utilities. They did a very bad survey, and in the end, they had to move dozens of lines. So moving the lines, think of it as the construction company that's already in the field suddenly finds new lines. So worst case scenario, they hit them and die. But there's insurance for damages. But what is not insured is, okay, I found 15 power lines. What do I do with them? You have to call the companies. You have to get the permits to move them. You have to find out where you're going to bury them again. It's called relocation. You have to do all of this while the entire project stops. So it was a 6-month delay. For the first time, they encountered different lines, and it happened over and over again. So first of all, it's huge delays. And second of all, it's not the fault of the contractor. The contractor is going to come back and say, hey guys, I didn't work. I have 500 guys in the field for you with 100 trucks. All of it stopped completely for 6 months because of wrong information you gave me. I want $500 million for those 6 months. That's what happens. So that's one story that actually happened.
Can I just make sure I heard you say something correct? You said they can hit those pipes and die?
It's very dangerous to hit. Hitting a gas pipe or a live power line is deadly.
Let's just stop there and say that was the worst story. You killed 2 birds with 1 pipe. So if I understand this right, the information that was collected, analyzed, and presented to the authorities and whoever was involved in the Seattle project was just wrong. How does that happen?
Because the technology they have is not good enough.
They're looking for pipes underground.
Pipes and...
But there's not new.
It's all pipes. All pipes underground. They need to know where they are. And they're looking to know also if it's sand or rock. Like, what's going to be the project? Like, in what are you digging?
But these techniques and these questions are not new, right? The subways have been around for a long time.
They were all over budget and over time.
Well, we're paying for that.
Of course, it's all public money. The technology today, there's a set of tools, of sensors that are used to map the underground, and there's a lot of heavy drilling involved. So it's 2 different sets of tools that are used, and the map is usually a combination of those 2 things. If you have better technology, then you dig less. If you have zero technology, you dig a lot. But in the end, that's how you build a map. This combo is not good enough.
The map is the assessment of professional who are the companies or the professions who gather information and present that assessment?
It's engineering firms, and they bring in digging companies that have those trucks that can dig very fast to find stuff. And they have surveyors, which are other companies that they call that have all the technological tool. In those complex projects, the projects where we're working, it's the engineer who belongs to a very big engineering firm, who are the consultants to the owner, who are in charge of creating the map. And then this map is part of the information that's going to be in the bid. They write a big bid of what's the project, and then contractors have to price it. And this is part of the information in that bid.
And that's critical information that forms the bedrock of the entire process, which says, you see this whole structure, everything underneath it is
or not good to go, but you will have to move 4 power lines. You know that you can move them here. You can think of how much it's going to cost and then price it. In the end, there's a lot of complex things. There's also a lot of complex things above ground, huge, but they're well mapped, which means the information is correct. With underground, it's the Achilles of this thing, because it's like the information is partial, and you will discover it so late in the project, it's going to cost a huge amount of money to correct.
Right. You're describing a group of people, engineers and surveyors. There's a whole industry around mapping the underground.
Correct.
And the technology is not good enough, even though I'm sure that consultants and engineering companies working on really big projects must have at least a solid idea that they know what they're doing, they have a reputation, but still the methods that are being used and the tools that are being used now to map the underground, are they being innovated, or they're not being innovated? Have they changed or they're not changed? Just take us into the evolution of those tools.
They've been constantly evolving, slowly, but constantly evolving. There's a lot of startups also in this world. And I believe that they took the maps from 50% to around 70, 80%, which is the maximum they can reach, those consultants. With all the technology, they can bring in as much technologies and surveyors and digging as they want. They will never get to above 80%. That's from the statistics that we have. We did 60 head-to-head competitions with what we call status quo in the last year and a half. And the range of additional lines we find is always between 20% minimum to 100%, like twice as much, depending on the quality of the technology and the effort and money they put to create that map.
And you're taking that next step into that 20%, which is the certainty based
So
on
we say we're
observation.
99%, which means we're basically 20 times better than the alternative, because what's important is how much did you miss? 20% versus 1%. That's the difference.
Even on the big projects, even on the big, well-funded, well-resourced government projects, infrastructure projects, they still miss stuff.
20% if they're very good.
And that 20%, more often than not, leads to months and potentially worse, longer overruns and complete budget breakdowns and everything. Before we talk about how you do that 20%, maybe I should have done this earlier, but why should people who are not in construction, development, transportation, why should they care about what Exotigo is trying to fix in construction? We spoke about a private market and a government market, but is there a connector?
Yeah, there's two connectors. One, in the market where we're active right now, there is an interest for the public to have those projects which are kind of ruining their day-to-day lives. A construction project it's not fun for years. There is a very high interest from the public that it lasts only 5 years and not 8, this disruption to day-to-day life. And in the end, there's a taxpayer interest that those projects finish on budget and on time. Those projects are amazing for the population once they're done, which is an additional factor. So that's current. Energy also. Everybody has an interest to switch to net zero fast. As a humanity, we have an interest for that. And on budget.
Sorry, I didn't understand the connection to climate.
The two biggest budgets that are around here right now for infrastructure are transportation, which is one, and electric, switching to net zero. There's huge government funds for billions of dollars. They're building a lot of new stations. Their way of creating power is now green. That's a government incentive. They've been financed for that, and it's happening all over the world. So those are also type of projects that we're working on, big electric projects.
What does that look like? That's taking a coal power plant,
transforming it, for example, or building a totally new station and then connecting those stations. It's called the grid. Expanding the grid, burying more power lines everywhere.
So there are going to be blueprints and plans that say, here's the old building. 2 miles away, there's a new building. We're going to connect those buildings with these pipes underground. We've checked.
And a bit like fiber optics. Suddenly, the cables in Tel Aviv are not enough for all this electricity. So you need to double the number of cables. So you need to bury a lot more cables in the city. That would happen too. It's called grid expansion.
Okay. All of this, it ladders up to more taxes for us to service bad planning. Things overrun. We don't actually get to feel the benefits of those projects in time.
Yeah.
That hits productivity, time wasted, time in traffic, all sorts of things, which just hits the overall economy. And so we should care about the inefficiencies at the base of construction
and the disruption to your life as a citizen when your street is blocked for 10 years. And the project might have lasted 5 if it was done more efficiently.
Let's just tell people what Exotigo does, because we know that it's looking for that 20%, that stuff that people miss, the surveyors miss. Take us into the genesis of the company. What is their technology? How does it work? Where did it come from?
The idea actually came from when we were thinking as founders to do a startup in the medical world. And the concept that hit me is, why is there an MRI and an ultrasound and a CT scan and an X-ray It's 4 different devices, 4 different doctors, 4 different pictures. Why? When you deep dive into this question, you discover that it's the same exact problem for underground. And it's because the world of imaging, I call it imaging, it's where a camera doesn't work. The world of imaging is ruled by hardware companies who are very, very good at building one sensor of one specific type, cutting edge sensor, and believing and selling it as if it solves the whole problem. But the sad truth is that there's no silver bullet for imaging. The way of reaching those 20% more like we do is we took the approach of saying, okay, we will do everything all the time. We're going to do an X-ray and an MRI and a CT scan and an ultrasound. And then we're going to create one 3D image out of all of it. And we're going to replace the doctor also with AI.
Dr. White. Dr. White, call your office. Dr. White.
And this is a combo we chose for underground utilities. For every problem, we have a different combo. But basically, this combo has 4 physical sensors, which you can think of them as the CT scan and the MRI and the ultrasound. And they have all those names, GPR, EM, MAG, MD, existing sensors. But there's also additional sensors like computer vision, which is images. Records means we search online. The web is a sensor for us. We might find records, we might find images of open trenches and manholes. We search for pictures and plans that maybe somebody uploaded this year, last year, 50 years ago, satellite images from all the years, Google Street View, you can have a photo of every year from Google, and then visual indications from the field also. There's a lot of things above ground that help you understand the story of what's underground, like manholes, electric boxes. We need all of that. And once you've collected all that information, then it's uploaded to the cloud. It's 500 gigabytes per acre of data. It's huge amounts of data. And that's where it becomes complicated. Taking those 500 gigabytes per acre of data, completely different types of data. Think of all what I just said we collect. And merging them to a single source of truth is extremely hard. You need a huge cloud database, which means everything that those devices do in the field is recorded, labeled. We're training AI models on the data. We need everything to be completely labeled, ordered. And this is a very hard software problem to solve. And then the algorithms you need to actually combine this data and interpret it and transform it to a single map are state of the art. And I would call it, that's our real core IP, is a new type of AI that nobody does, which is called ultra low SNR signal processing AI. It's a nerdy name, but it's something very hard. Yeah.
Let's do that again slowly.
Ultra low SNR.
Ultra low SNR.
Signal to noise ratio.
Ultra low signal to noise ratio.
Signal processing.
Signal processing.
Which means we look at the data and basically you can't see anything in the data, but you still need to find what's there. That's the type of algorithms that we develop on a lot of different sensors.
And this is your main IP. You build the devices, you deploy them, they upload data to the cloud. Your algorithms, which also combine crawling on websites and public records, really triangulates all of the data. This is where the hard stuff is, right? In my experience, also very hard to explain. Could we try an analogy? So all this data is coming, it's from different types of hardware, which is really hard. It's just completely different data. There's depths, there's sound waves, there's cameras, there's internet research. Take us into the machine.
There's three main machines, I would say, sorry. One is just the sensors, the physical sensors. Think of it as an ultrasound data from different types of devices. This is one algorithm that takes the stack of those and creates a map of objects it sees. Disturbances in the signals. So that would be one family of algorithms, very huge family.
That's like a disturbance in the force.
But you have to find it in multiple sensors. So this is called the geophysics AI. Think of it as like finding oil or finding gold to be the same type of algorithms. They search for patterns in the signals.
The signals can be piped under the ground. How does the algorithm know
Because
that
the physics, if you have a pipe underground, it will affect all the different types of physics somehow. And so there's a lot of brain there of maybe I should know how it will affect and I'll use simulations in my AI. Maybe I don't. Maybe I search brute force for disturbances. There's a whole family of algorithms we do to discover weird stuff in the signals.
Because the show is called The Dejargonizer, and I really appreciate your patience. I'm trying to get an analogy here of when you said the algorithm figures this out from all of the data somehow, it's not good enough. Even if we don't know the technical, we can't get into the technical stuff. Is there an analogy? Is
I have
there
an idea.
something?
Let's take a doctor watching an ultrasound and having to say if the baby is okay. And you want to solve that with AI. There's two approaches, which we mix. One is learning the brain of the doctor and what he looks at when he looks at the baby to say, this is okay, this is not okay. This is using physics, understanding why the doctor says it's okay or not okay. You could teach it.
What the doctor sees with their eyes and the experience
they have, and they know that if there's a tweak here and a twitch here and this, then it means that this and this. This would be one way of copying the doctor. The second way is saying, which is a bit more classical AI, but it's saying, I don't know, I'll take 10,000 pictures of ultrasound and I'll teach an algorithm that this is the standard. And then if it deviates, tell me there's something unusual. So those two methods need to be applied in our area so that you get a good result. We already have like 1,000 sites around the world, and every time there's a scan in the world, it adds, and the AI can train more and more. And we're constantly expanding our database. The second area is doing records and computer vision, which is way more classical AI. And then the third machine is the one that takes the sensors they map, what we call metadata, which is computer vision and records, and then uses the records and the computer vision to understand what did the sensors see. What is this black line? Is it a gas pipe, a power line, or something else? And that's how we solve the problem, basically. Sensors, any data we can gather with more classical ways, combining.
Great. How far ahead or how different is that from the best current other methods, traditional methods of surveying? What tools are they using?
They would use one or two of the sensor package that we use, and then they don't have the software that we have. So I would say they would collect like 10% of the data we collect, maybe at most, and they would use humans to interpret all of it. We leave no room for human interpretation, which means we're making a product so that anyone can scan with it and it doesn't affect the result. And that's why it's a software product, which means the screen tells you live where to go, what you still have to do, if the sensors are working okay, all the data is uploaded to the cloud, and all the decisions are made in the cloud. Basically, it's like saying you don't need to be a photographer to take a picture anymore, and our picture will be way better than if you bring the photographer.
Your deployment with the national grid, just give us the top lines of that.
So that was a pilot we did at the beginning, where they did what they do typically, brought surveyors, digged, and then we came in and we found a couple of major lines that were where they were supposed to dig that were not picked by their survey. This specifically was a gas project in New York. They were burying a new gas line in New York. And so the data we provided changed their plans, which means the project was changed because of the data we provided, and we provided it on time. So it was a very good pilot, and now we're deploying on a number of projects in National Grid commercially.
Excellent. The last question, which I think will also take us into what's around the corner, what's over the horizon. You mentioned pods, about people being able to scan themselves. Just talk to us about that.
Two major lines of expansions that we're doing. One is the same scan will produce also, and it's already started, but elements of grounds and not just pipes. Voids, sinkholes, is it sand or rock, water table, a lot of other interesting and very hard questions to answer. So that's one expansion.
Granular. It's
way
more
more
granular.
granular. That's what we're really building. You would have a combo. The next completely perpendicular expansion is saying, okay, this is our full service market for those big projects with big contracts, recurring ones or for years. But then we want to use the same technology and create, I call it the Exapod on Amazon, which means you're building a pool in your backyard.
Tim, what? I'm Cat, what?
You would be able to order it, scan your backyard with it yourself, send it back, and get a map to your phone on Google Maps of what's underground and can you build your pool there.
Jeremy, thank you very, very much for your time.
Much. Thank you so much, Amir.
More accurate mapping of underground utilities affects all of us. This episode provided an inside look at a complex industry ripe for an efficiency revolution. It showcased how smart software and data analysis can transform traditional sectors to make them safer, faster, and more cost-effective. Even those not directly involved in the construction business are impacted by these inefficiencies through higher taxes, delays, and infrastructure problems. Thank you for listening to the Dejargonizer. If you liked the episode, please leave it a review on your favorite podcast app. And I'll be back soon with more Dejargonizer sessions.